Let's jump into some insertion operation. So in order to insert, you need to make sure that the next valid leaf position you're gonna be inserting at, it must be to have a complete binary tree. Like I said, heap has two main idea. You have to keep its property. Second, you have to make sure it is a complete binary tree. So you need to know the next valid leaf position. This is the location where you're gonna be inserting your node. And by the way, leaf here is gonna be like the last last element in your tree. This is the point of the leaf. Like the leaf node, right? The actual leaf node here are 0 and -5 and 2. Those are the leaf node right now. So the remaining leaf, which is currently empty, is the right side of 3. This is the next valid leaf position. So let's say now we're gonna be inserting a node with value 1. So this is a valid position right now. Now we need to heapify. What does heapify mean? We need to bubble up or bubble down in order to make sure that the current heap is valid or not. So after we have inserted right now, at this position, 4 is greater than 2 and 3, 2 is greater than 0 and -5, 3 is greater than 2 and 1. So basically we don't really need to do anything, even so we needed to heapify, but we didn't really do anything. Why? Because currently in this position, it is already complete binary tree. It have its correct property. So basically we don't really need to do much. What happened now when we try to insert a node with value 8? And if you have seen right now, we have a complete binary tree. We can't really add anything to the children of 2 or 3. So, and we have level 3 now is complete. So what we're gonna do, we're gonna be inserting to the left side of this 0. So what happened, we're gonna be inserting a node at this valid leaf position, which is starting from the left position of this 0, which is our 8. So currently we're in a maxi heap. So is this 0 greater than or smaller than 8? It is actually smaller than. This kind of invalid heap. This is not right. You can't really have a parent that is smaller than its children in a max heap. It is not the property of the max heap. So we need to heapify. How can we heapify this? We're gonna be checking that this node we have inserted. It is 8. Is 8 greater than 0 or not? Its parent is 8 greater than its parent. It is actually greater, so we're gonna be replacing. Is this 8 greater than its parent or not, which is a 2 now? It is actually greater than, so we're gonna be replacing. Is 8 greater than its parent, which is 4? Is it greater or smaller than? It is greater than. 8 is greater than 4, so we're gonna replace it. So 8 currently is the node. Is there any parent other than this 8? No, there is not. And this is a valid position at this point. So now if you have checked, is this 8 greater than 4 and 3? Yes. Is 4 greater than 2 and -5? Yes. Is 2 greater than 0? Yes. Is 3 greater than 2 and 1? Yes. This is a valid heap and a complete binary tree. So now what happened if we try to insert a node with value 6, for example? What happened? We need to insert to the valid position. We're starting from left to right. So we have started with 0. And now we're gonna go to the right side of this 2 because the left side is complete here. So now we have inserted 6 and 2 is smaller than 6. Doesn't make sense. This is wrong. You can't have this in a max heap. 2 can't be smaller than its like the parent can't be smaller than its children. So we need to heapify. How can we heapify? Is 6 greater than 2? Yes, we're gonna be replacing. Is 6 greater than 4? Yes, we're gonna be replacing. Is 6 greater than 8? No, it's not. So we're gonna keep it this way. And this is the idea about heapifying and this kind of stuff.